Welcome to another deep dive. This time, we're going down the rabbit hole of quantum mechanics.
Buckle up.
You sent us a fascinating transcript from a YouTube video
Yeah.
about this big debate, really, between Albert Einstein and Niels Bohr about the nature of reality itself.
It gets kind of deep. Like, does the universe exist if we're not looking at it? That kind of question.
Exactly.
Gets pretty philosophical, which I love.
It's mind-blowing stuff, really. So before we get into the debate itself, let's just kind of recap what makes quantum mechanics so strange, so counterintuitive in the first place.
Right.
For people who maybe need a little refresher.
Yeah, so, it's basically the theory that governs, like, the really tiny world. Atoms and all the particles that make up atoms.
The subatomic world.
Exactly. And the thing is, it just completely throws out the window everything we thought we knew about physics from, like, our everyday experience.
Right, the laws of physics we learned in school about, how things move and behave and all that. Newtonian physics.
Exactly. Like, Newton's laws work great if you're talking about, like, throwing a baseball or driving a car, but they just break down completely when you get down to the subatomic level.
So what are some of the key principles of quantum mechanics?
Well, one of the most famous and probably the most mind-boggling is the uncertainty principle.
I've heard of it, but I'm not sure I fully get it.
Basically, it says you can't know both the position and the momentum of a particle with perfect accuracy. Like, the more precisely you measure one, the less you know about the other.
So it's not like our instruments are just not good enough. It's like there's a fundamental limit to what we can know.
Exactly. And it's not just that we can't know it, it's that the particle itself doesn't have a definite position and momentum until it's measured.
So the act of measuring it actually affects its properties.
Right. And that's just one of the strange things about quantum mechanics.
I am already getting a headache.
There's also this thing called wave-particle duality, where, like, particles like electrons or photons, they can act like both a wave and a particle.
It's like, how can something be two things at once?
It's weird, I know. It depends on how you observe it. There's this famous experiment, the double slit experiment, where, like, they shine light through two slits.
Okay.
And if you don't try to measure which slit each photon goes through, they create this interference pattern like waves. But if you try to measure which slit it goes through, it acts like a particle and the pattern disappears.
Wow. It's like they know we're watching.
It's almost like that.
Yeah.
The act of observation forces them to choose.
No wonder Einstein had issues with this stuff.
Oh, yeah. He did not like it one bit. He was a realist through and through.
Meaning?
He believed that the universe exists objectively, regardless of whether we're observing it or not.
Oh, like the moon is still there even if I don't look at it.
Exactly. That's actually a famous quote of his.
Well, it makes sense. I mean, that's how we experience the world, right?
Right. But quantum mechanics says not so fast. It introduces this inherent randomness, this uncertainty that just didn't sit well with Einstein.
Because he was looking for order in the universe?
Yeah. He famously said God doesn't play dice. Like, he believed there had to be some underlying deterministic laws governing everything.
Hidden variables or something like that?
Exactly. He saw quantum mechanics as a useful theory, but an incomplete one.
Like it's just a stepping stone to some deeper truth.
Right. He spent much of his later years searching for a unified theory that could, like, reconcile quantum mechanics with his own theory of relativity.
So he never really bought into this whole uncertainty thing.
Nope. He was convinced there had to be a better explanation.
And so on the other side of the ring, we have Niels Bohr.
Yes. Niels Bohr, the champion of the quantum world.
Tell us about him.
He was a Danish physicist and, like, one of the key figures in developing quantum mechanics. And unlike Einstein, he fully embraced uncertainty.
So he was okay with the idea that there are some things we just can't know for sure.
Absolutely. He said we shouldn't try to force our classical intuitions onto the quantum world. We need to let the data guide us.
So he was more of a pragmatist.
Yeah, you could say that. He was all about, like, what can we actually observe and measure?
Yeah.
And he believed that the act of observation is an essential part of quantum phenomena.
It's not just a passive thing. We're actually changing the world by looking at it.
In a way, yes.
Yeah.
He developed this concept called complementarity.
Yeah.
Which says that certain properties, like the wave and particle aspects of light, are complementary.
Meaning?
You can observe one or the other, but not both at the same time. It's like two sides of the same coin. You can't see both sides at once.
Okay, I think I'm starting to see where this is going. Two brilliant minds, two very different ways of looking at the universe.
Exactly.
Yeah.
And their clash of perspectives led to some of the most fascinating debates in the history of science.
So let's talk about those debates. How did this clash play out?
Well, their first major confrontation was at the 1927 Solvay Conference.
I've heard of this. It was like a meeting of the Avengers of physics.
Exactly. All the big names were there. Einstein, Bohr, Marie Curie, Max Planck,
Wow. A who's who of physics?
and Einstein. Well, he came prepared to try and dismantle the uncertainty principle.
He went on the attack.
He sure did. He presented a bunch of thought experiments, these ingenious scenarios designed to show that there must be a way to, outsmart uncertainty and know both a particle's position and momentum at the same time.
So, he was trying to poke holes in quantum mechanics.
Exactly. But Bohr wasn't just going to sit back and watch his theory get demolished.
And he fought back.
Oh, he did. For each thought experiment Einstein presented, Bohr carefully analyzed it and showed how, nope, the uncertainty principle still held.
It must have been an intellectual battle for the ages.
It was, like a chess match between two grandmasters, each move forcing the other to think more deeply about the nature of reality.
So this Solvay conference, it sounds like it was a real turning point in the debate. Einstein trying to dismantle uncertainty and Bohr defending it. What happened next?
Well, the debate didn't end there.
Yeah.
Einstein, he was a persistent guy.
He wasn't going to give up that easily.
Nope. A few years later, in 1930, he came up with another thought experiment. This one's called Einstein's box.
Okay, Einstein's box. What is that?
Now, imagine a box. It's filled with radiation.
Okay.
And there's a clock inside that controls a shutter, which can release a single photon. So Einstein said you could weigh the box before and after the photon escapes.
Right.
And by doing that, you could determine both the photon's energy and the exact time it was released.
So he thought he'd found a way to measure both those things with precision.
Yeah, which would seemingly violate the uncertainty principle.
So, he thought he had outsmarted quantum mechanics.
He thought so. And at first, even Bohr was stumped.
Oh, wow. Even Bohr couldn't figure out what was wrong with it.
Yeah, it was a pretty clever thought experiment.
Huh.
But then Bohr had this epiphany.
Uh-huh.
He realized that even Einstein's box couldn't escape uncertainty.
How so?
Because to weigh the box, you need some kind of scale, right?
Right.
Like a spring scale.
Okay.
But when you weigh the box, the spring moves slightly,
Uh-huh.
which means the box's position is also uncertain. And according to general relativity,
Einstein's own theory.
exactly, gravity affects time. So an uncertainty in the box's position.
Leads to an uncertainty in time.
Exactly. Bohr used Einstein's own theory against him. It was a pretty amazing moment in the history of physics.
Wow, so even Einstein's attempt to disprove quantum mechanics actually ended up supporting it.
Yep. But the debate didn't end there.
Of course not. They couldn't leave it at that.
Einstein wasn't convinced. And a few years later, he came up with his most famous challenge to quantum mechanics,
What was that?
the Einstein-Podolsky-Rosen paradox, or EPR paradox for short.
Okay, I've definitely heard of that. Something to do with entanglement, right?
Exactly.
That's where things get really weird.
It does. So entanglement.
Yeah, what exactly is entanglement? In plain English.
Okay, so imagine two particles, let's say two photons.
Mm-hmm.
They're created together in a way that their properties are linked.
Okay.
So one is spinning up and the other one's spinning down. But you don't know which one is which until you measure one of them.
Okay, makes sense.
But here's the weird part. If you measure one photon and find it spinning up, the other one instantly becomes spin down.
Wait, what? Instantly?
Yeah.
Even if they're miles apart?
Yep. It doesn't matter how far apart they are. It's like they're connected by some invisible thread.
That is so bizarre. It's like magic or something.
I know, right?
Mhm.
Einstein called this spooky action at a distance.
And he did not like it.
Nope. He thought it was ridiculous. He said it violated the principle of locality, which means that something can only be influenced by things in its immediate surroundings.
You can't kick a ball on Earth and have it instantly move a ball on Mars.
Exactly. Einstein believed that there must be some hidden variable, some underlying mechanism we haven't discovered yet, that explains how these particles communicate.
So, they're not really communicating instantly. There's just some information we're missing.
Exactly. He thought quantum mechanics was missing a piece of the puzzle.
But what if he was wrong? What if this spooky action is real?
Well, that's the thing. Experiments have shown that entanglement is real.
Really? They've actually proven it.
Yep. There have been numerous experiments, especially since the 1980s, that have confirmed the predictions of quantum mechanics.
So Einstein was wrong.
Well, it's not that simple. Einstein's objections to quantum mechanics were, like, really important. They forced physicists to think harder about what the theory really meant and to develop more sophisticated experiments to test it.
So his skepticism actually pushed the field forward.
Exactly. And, the EPR paradox,
Yeah.
it really gets to the heart of what we mean by reality.
Yeah, if two particles can be linked across vast distances, what does that say about the nature of space and time?
It's a question that's still being debated today,
Uh,
and it has led to some pretty wild interpretations of quantum mechanics.
like what?
Well, one of the most famous is the many worlds interpretation.
Oh, yeah, that one. I think I read about that in a science fiction book once.
It does sound like science fiction, but it's a serious contender among physicists.
So what is it exactly?
It basically says that every time a quantum measurement is made, the universe splits into multiple branches.
Wait, like parallel universes.
Exactly. In each branch, a different outcome of the measurement occurs.
So, like, there's a universe where I decided to wear a blue shirt today and another one where I wore a red shirt.
Yep, something like that.
Wow, my mind is officially blown.
It's a pretty mind-boggling idea, I know. But there are other interpretations too, like pilot wave theory.
What's that?
It's a deterministic interpretation of quantum mechanics, kind of like what Einstein was hoping for.
So maybe he wasn't completely wrong after all.
It's possible. But the debate goes on, and it's one of the most exciting and thought-provoking areas of science today.
So, wow, we've gone from uncertainty to wave-particle duality to entanglement, even parallel universes. It's a lot to take in.
Yeah, it's pretty wild stuff, right? But that's quantum mechanics for you, always pushing the boundaries of what we thought was possible.
And all stemming from this debate between Einstein and Bohr. So where we land on that? Who won?
That's the thing. I don't think it's really about winning or losing. The debate is still going on today. Physicists are still exploring different interpretations of quantum mechanics.
Yeah, trying to figure out what it all means. Like, what does this tell us about the nature of reality itself?
Exactly. But what's undeniable is that the Einstein-Bohr debate really shaped the course of physics. And not just physics, actually.
What do you mean?
Well, the idea that the observer plays a role in shaping reality. It's had a pretty big influence on other fields, like neuroscience, for example.
Okay, so how does quantum mechanics relate to the brain?
Well, think about it. Our brains are these incredibly complex systems, billions of neurons firing all the time.
Right.
Some neuroscientists are starting to think that maybe, just maybe, quantum processes might be involved in how our brains work.
So, like, the same principles that govern the behavior of particles could also be at play in our thoughts and feelings.
It's a radical idea, I know, but it's not completely out there.
I mean, if the act of observing a photon can change its state, could it be that our consciousness, the act of observing our own thoughts, somehow influences the physical processes in our brains?
That's the question, isn't it? And it's a question that takes us right back to the heart of the Einstein-Bohr debate. What is the role of the observer? Can we ever truly know the universe independent of our own perceptions?
It's almost philosophical, like, does a tree falling in the forest make a sound if no one is there to hear it?
Exactly. Quantum mechanics really blurs the line between the observer and the observed.
So it's not just about equations and experiments, it's about grappling with some of the deepest mysteries of existence.
And that's what makes it so fascinating. It forces us to rethink what we thought we knew about reality. And it opens up whole new avenues of exploration, not just in physics, but in other fields too.
Well, this deep dive has definitely left me with more questions than answers, but that's a good thing, right?
It is. It means we're on the right track.
Keeps us curious.
Exactly.
So, to our listener out there, if you're feeling a little mind blown right now, that's perfectly normal. Quantum mechanics is weird, but it's also incredibly exciting. It's a reminder that there's still so much we don't know about the universe, and who knows what incredible discoveries await us in the future. Until next time, keep exploring, keep questioning, and keep diving deep.